Dear students, our today lecture is about the wave functions, electronic configurations, and the binding energy for the multi-electron atoms. As here we will discuss that what are the differences and what are the similarities in the multi-electron systems and the one-electron systems. As one-electron systems like hydrogen atom we have already discussed in our previous videos and in our previous lecture. So now we are going to discuss about the multi-electron atoms. The wave function and binding energy for the multi-electron atoms. So here are some differences and there are some similarities, and so the first thing is that the Schrödinger wave equation. Schrödinger wave equation correctly describes the electronic structure for all of the atoms. And secondly, the multi-electron orbitals are similar in shapes and we have the same nodal structures as corresponding to the one hydrogen atom like one electron orbitals. This means that whether we are talking about the one electron systems or either it is the multi-electron systems, we have the same orbitals, same shapes of the orbitals. Like we talk about the s orbitals. S orbitals we have already discussed in our previous lecture, that is it is always spherically symmetric. That is, we have the probability out or in the value direction of or except at the radial planes, radial nodes. So except at the radial nodes we have the probability of finding the electrons spherically out spherically symmetric. So it's the electron s orbital is the same whether it is the one electron systems or it is multi-electron system. And let's talk about the p orbital. P orbitals, which have the which are we can find the p orbitals in three different directions, like the px orbital, py, and pz orbitals, and so we have the nodal planes. uh, in case of p orbital, that is like the angular nodes, and shape of the nodal planes and the shape of p orbital always remains the same whether it is the one electron system or it is a multi-electron system. So the shape of orbitals and correspondingly the nodal structures remains the same for one electron like hydrogen atom or multi-electron system. So these are the similarities between the one and multi-electron atoms. And so what about the differences? However, there is the important differences in thinking about the multi-electron binding energies. Okay, so when we talk about the binding energy, this means that now there are the it's different for the one electron system and for the multi-electron system. So the states in the multi-electron one electron systems are always higher in energy than their corresponding states in the multi-electron systems. So in coming so we are going to discuss why it happens, why the multi-electron energy levels are always lower in energy than their corresponding levels in the one electron system. So all orbitals in multi-electron atoms are lower in energy than their corresponding orbital in the hydrogen atom, as we have already discussed the energy levels of hydrogen atom. So here we have the one electron system, that is like the hydrogen atom. Here you can see that this is the first energy level. In first energy level we have the 1s state. In second energy level we have the 2s and 2p state, that is 2px, 2py, and 2pz states. And up here we have the third energy level, we have the 3s, 3p's, and 3d's, and then fourth state 4s, 4p, 4d states. So here the important thing to notice here is that here you can see the degeneracy in the orbitals. That is, in second energy levels, you have the 2s and 2p states. In 2s and 2p states, both are in the same energy state. Both are degenerate state. These are the degenerate orbitals. That is, they are in the same energy state. As we go up in the third energy level, again you can see here that all 3s, 3p's and 3d states are in the same energy states. All are degenerate energy states. So in one electron system like hydrogen atom, we have the degeneracy in the energy levels. These are in the same energy state. So the difference is in the multi-electron system when we consider the multi-electron atom. Multi-electron atom, here you can see that we have first we have the 1s state, and then we have the 2s, then 2p state, which is 2px, 2py, 2pz. Up there we have 3s and 3p states, 4s states, so on. So here you can see that the main difference here is in the degeneracy of energy levels. So the degeneracy in the energy level, as the states in the one electron systems are degenerate, while in the multi-electron system these states are non-degenerate. Here we have the 2s and 2p states are in different energy states, while in the one electron system they are in the same energy states. In the same way, when we go to n is equal to 3, third energy level, we have the 3s and 3p states are in the are separated by some energy difference. That is, they are non-degenerates. They have the different energy states, while in the one electron system all 3s, 3p and 3d states are in the same energy states. But in multi-electron system we have 3s, then we have the 3p, then 4s, and then we have the 3d states. So there is a separation. Energy levels are separated by some energy difference. So these are the non-degenerate energy states. So another important thing to notice here is that all states in the multi-electron systems, in the multi-electron atoms, in the all states, that is 1s, 2s, 2p, 3s, are lower in energy than their corresponding states in the one electron system. So this means that 1s state of multi-electron atom is lower in energy than 1s of one electron system. That is, it's more negative or more lower in energy as compared to the 1s of one electron system. In the same way, when we go to the 2s state, again the 2s state, it is lower in energy than the 2s of corresponding one electron 2s states. So it's more lower in energy or more negative as compared to the 2s of one electron. So in the same way, you can see that 2p states again lower in energy as compared to the 2p states of one electron system. So it means that all these states are lower energy. So now what's the reason why the states in multi-electron atoms are lower in energy as compared to the corresponding states of one electron system? The reason is atomic number. That is, Z as for one electron system which has Z is equal to 1. But for the multi-electron atom, Z is more than 1. So it means that the atoms in the multi-electron systems are experience the more positive charge of the nucleus. Nucleus is more positive in the case of multi-electron system. When there is the more positive charge, it means that orbitals are experiencing the more positive force of the nucleus. So it's a kind of attracting all the orbital towards the nucleus. So all orbitals become closer to the nucleus as compared to the orbitals in the one electron atom. The orbitals in the multi-electron atoms are experiencing the more positive charge of the nucleus, they come closer to the nucleus, and that's why they become lower in energy. They becomes the lower energy, that is 1s is, here we can see that 1s of the multi-electron system is the more negative, means that the electron in the 1s of multi-electron atoms are more tightly bound to the nucleus as compared to the electron in the 1s atom of one electron system. So in the same way, in the other orbitals like 2s, 2p, 3s, they are lower in energy. Lower in energy means that they are close to the nucleus and experiencing the more negative, they are more negative binding energy, means that more tightly bound to the nucleus as compared to the one electron system. So in the same way, here you can see that 3s all are lower in energy than their corresponding orbitals in the one electron system. So we can summarize like that: the lower energy results in the multi-electron atom results from the higher Z number. Higher Z numbers mean that stronger pull from the nucleus. Nucleus is strongly attracting all these orbitals toward itself, and that is they are coming close to the nucleus. As a result, they becoming the lower in energy. So this is the way in which the binding energy plays role in the orbital energies. So the next is that is now the principal quantum number n. This means that's no longer the sole determining factor for the orbital energies of multi-electron atoms. So the binding energy is now depends on the value of NL. So it's not only depends on the principal quantum number, now it also depends on the orbital quantum number L as well. So it means that now orbital quantum number matters. Now how it matters? Now have a look at the equation like binding energy. This is for one electron atom. So binding energy for the one electron atom is equal to the minus ionization energy, and it's equal to minus Z square. Z is the atomic number, into Rydberg constant or H over N square. Now if we look at binding energy of multi-electron atom, it look pretty much same. Like again, it's the binding energy is equal to the minus ionization energy, but difference here is that now it's not only depends on the value of n principal quantum number, but it also depends on the value of L as well. Now the n and L, that is principal quantum number and orbital quantum number, together determines the binding energy, that is equal to the minus ionization energy. Now it will be equal to the minus Z effective square over N square into Rydberg constant. So it means that here another difference is that here we use the Z atomic number and here we use the Z effective, that is Z effective here, which abbreviated as ZEFF. It represents the effective charge. Now we will discuss the effective charge. This effective charge is due to the screening effect. Z effective is the effective charge experienced by the electron in the n and state. So for the specific n and orbital quantum numbers and principal quantum number represent the specific states where the Z effective is effective charge experienced by the electron. So we see effective the same as Z for the nucleus. The Z effective differ from the Z in fact in terms of screening effect or shielding effect. Now we will explain what is the shielding effect or what is screening effect. So the shielding effect and effective charge. So to illustrate the shielding effect, here we will consider the two extreme shielding situations possible for the helium atom. For helium atom, this is another extreme of the periodic tables, that is for Z is equal to 2, and this means that shielding, as we know that in the case of atom we have the two types of electrons. We have the core electron And we have the valence electron, the core electron, which experience the full charge of the nucleus, and that is cancelled out by the positive charge of the nucleus, and so the valence electron experience the remaining charge of the nucleus, and so that charge is called as effective charge. So it means that core electron shield the outer electron from the positive charge of the nucleus. So here, to explain the shielding effect or screening effect, here we consider the two extreme shielding situations which is possible for the helium atom. So for the first case, here we consider the helium atom Z is equal to 2. So for Z is equal to 2, it means that helium atom have the charge equal to +2, and so it has the 2 electron 2, and this one is the electron 1. Here you can see that in this case we consider the electron 1 is away from the nucleus, and electron 2 is close to the nucleus. So when electron 2 is closer to the nucleus, it means that it experiencing the full charge of the nucleus, experiencing the full force of the nucleus is acting on the electron 2. So now we are interested here in electron 2. That is how electron 2 shield electron 1 from the nucleus, or how it shield the nucleus from electron 1. So here we consider the electron 2 just a kind of electron that it's totally shield or totally protect the nucleus from around everywhere from electron 1. So it means that the negative charge of electron 2 is completely cancelled out by the positive charge of nucleus. So electron 1 here, which is away from the nucleus, so electron 1 is now not going to feel Z is equal to 2. Instead it feels Z is equal to 1. So Z is equal to 1 is the effective charge here. So it means that electron 2 shield the nucleus from electron 1, or shield the electron 1 from nucleus. So it is called as shielding effect of electron 2. So here we can explain it like that. The helium nucleus has the charge equal to +2. So the electron 2 here, it is the case of maximum shielding. Maximally shield the electron 1 from the positive charge of helium nucleus. So it's maximally shielding. Maximally shielding means the maximally protecting the electron 1 from the nucleus, positive charge of the nucleus. So electron experience a force on the average of Z effective is equal to 1, not Z effective is equal to +2e. So here what will be the binding energy of electron 1 here? So in this case, as we know that the binding energy of electron 1 will be equal to the minus ionization energy. So as we know that is equal to Z effective square times Schrödinger constant over n square. So when we plug in the numbers over in the equations, you can see that it will be equal to the 1. Z effective is equal to 1 over 1 square to Rydberg constant. So it's just equal to the negative of the Rydberg constant minus 2.18 times 10 to the raised power of the 18th of joule. So it experienced the force just like it's a scenario of one electron system like hydrogen atom. So it's experienced the binding energy of just equal to the negative of Rydberg constant. Okay, now we go to another extreme case, that is case 2, that is another extreme. Here we consider the electron 2 is far away from the nucleus and electron 1 is close to the nucleus. So again our center is electron 2. Again we are interested in electron 2. That is, now the electron 2 is far away from the nucleus. It means that now it has no role in shielding electron 1 from the positive charge of nucleus. So it is far away, so it's out of the range of the nucleus, and so it has no role in the shielding. So this is another extreme case of no shielding. First case was of the of maximum shielding, and now this is the case of no shielding. In first case, electron 2 maximally shield the electron 1 from the charge of nucleus. Now in this case, the electron 2 is far away from the nucleus, so it's not going to shield the electron 1, even it's not participating in the shielding effect. So here the electron 1 experience the full charge of nucleus. So here the Z effective will be equal to plus 2, which is the full charge of the nucleus, which is experienced by the electron 1. So here the electron 1 have no shielding from the nuclear charge. So this is another extreme. So here this is the case of, again it is the case of one electron system but with the Z effective charge of plus 2, and it's like the scenario of helium plus. So we can explain it like this one. Helium nucleus, the charge is equal to plus 2e, and electron 2 doesn't participate in the shielding because it's far away from the nucleus, and electron 2 from the nucleus, the electron 1 experience the force on the average of Z effective is equal to 2. So instead of Z effective is equal to 1, which was in the case of maximum shielding, here the Z effective is equal to 2. So again we can calculate the binding energy of electron 1, and so here the binding energy of electron 1, again it is equal to the minus ionization energy, and it is equal to minus Z effective square into Rydberg constant over n square. Here the Z effective is equal to 2 and n is equal to 1. So here the binding energy for the electron 1 will be equal to the minus 8.72 into 10 to the raise power 18 joule. So this is the second extreme of no shielding for the hydrogen atom. Now we can summarize the two extreme cases. For extreme case A, where the electron 2 was shielding the electron 1 and electron 1 experienced the Z effective equal to 1. So in that case, the ionization energy of helium atom was 2.18 into 10 to the raise power minus 18 of joule. And in the extreme case B, where the Z effective was equal to 2, that is, now the electron 2 was out of the range of the nucleus, that it was the case of zero shielding or no shielding. So the electron 1 here experienced the full charge of the nucleus, so the effective was equal to 2, and in that case the ionization energy of helium atom was equal to 8.72 into 10 to the raise power minus 18th of joule. But in reality the situation is always between two extremes. So the shielding effect experimentally determined ionization energy is of the helium atom is 3.94 into 10 to the raise power minus 18th of joule, which is greater than 2.18 into 10 to the raise power minus 18 joule and less than 8.72 into 10 to the raise power minus 18th of joule. So we can calculate the Z effective, that is effective charge, from the experimentally determined ionization energy values. So when we have the experimentally determined ionization value, we can calculate the Z effective for helium atom. Okay, for helium atom, you know that its binding energy is minus ionization energy, which is equal to minus Z effective into Rydberg constant over n square. So from here we can calculate Z effective, which is equal to minus ionization energy and square over RH. So when we plug in the numbers, we get the value of effective charge for the helium atom is 1.34, as it is between these two extreme cases, that is between 1 and 2, it is 1.34. So effective charge of helium nucleus is helium atom is 1.34, which is experimentally determined value. So here now we are going to discuss more about the binding energy, that is how shielding effect, and that is how shielding effect or screening effect It has its impact on the filling of orbitals, on the order of orbitals. That is why the energy of 2s orbital is less than, that is, it is more negative than 2p, and then 3s is less than 3p and 3d. So now we are going to have a look on it. So for a given n state, that is for a given shell, the electron in orbital with lower value of L and lower value of orbital quantum number are closer to the nucleus, even though the most probable radius decreases with increasing the L. That is, the most probable radius for the S will be the greater than p orbitals. So, but we are not going to discuss about the most probable radius. Here we will discuss about the shielding effect. That is, the whole shielding effect have its impact on the orbital orders, or how we can order the orbitals in the energies, in terms of energies, uh, and in terms of energies, in terms of shielding effects. So first, here consider the most radial probability density versus radius plot, and this is for 2s and 2p orbitals. Here you can see the dotted line, and this one is the solid line for 2s. For 2s, as it is closer to the nucleus as compared to the 2p, although the most probable radius is longer for the 2s as compared to the 2p orbital, as the 2s penetrate deep into the nucleus and it's closer to the nucleus. Here you can see that it's closer to the nucleus as compared to the 2p. So 2s experience the less shielding, less screening as compared to the 2p orbitals. So the 2s orbitals are the more negative binding energy as compared to the 2p orbitals. So 2s energy of 2s is lower in energy as compared to the 2p orbital. So this means that for the same value of n, that is n is equal to 2, the s electron are less shielded than p electron. Thus E2s is lower than 2p states. This means that shielding effect has had importance in ordering of orbitals. That is, 2s orbital, which is close to the nucleus, has the less shielded by than the p electron, which are p orbitals electron, which are away from the nucleus as compared to the 2s. So 2s will be, energy of 2s will be lower than 2p orbitals. So here we consider n is equal to 3. When we go to the third energy level, we have 3s, 3p and 3d states. Here you can see from the plot that the 2s, again the radius of 3s, the most probable radius for the 3s is longer than 3p, but when we talk in terms of binding energy, here you can see that the 3s orbitals, again here these are more closer to the nucleus as compared to the 2p orbitals. As you can see that this is for the p orbitals, and 2s are more closer to the nucleus as compared to the 3p orbital. It means that 3s orbitals are less shielded as compared to the 3p orbital. Again, the 3s is lower in energy as compared to the 3p orbital, and because the 3p orbital has the less negative binding energy as compared to the 3s electrons. But as we go to the 3d orbital, again here the 3d orbital are away from the nucleus, away from the even from the 3p. So the 3d orbitals have much less shielding effect, experience the much less shielding as compared to the 3s and 3p orbitals. So these 3d orbitals are higher in energies. So we can explain it like the p electrons are less shielded than d electron. Thus the 3p E3p is lower in energy than E3d. So thus we can say that in a multi-electron atoms, the effect of penetration and shielding effect give rise to the order of orbital energies of orbitals. That is, how much is orbitals electrons are near to the nucleus, are penetrated to the nucleus, are have the effect of penetration and shielding effect, then they will be lower in energy as compared to those orbitals which are less penetrated into the shielding effect, or experience the less shielding of less force of the nucleus, or they are shielded from the nucleus, they experience the less positive charge of the nucleus, so they will be higher in energy. So we can say that shielding effect play the very important role in orbital energies. So we can say that shielding gives rise to the order of energy shell, that is S is less than 3, less than P and less than D, and it will be equal to the less than F orbitals. So now we are going towards the electronic configurations, that is how we can fill the electrons in the different orbitals on the basis of their energy levels. So the electronic configuration describes the electronic structure of an atom by specifying which orbitals are occupied. So these notations are very useful since the electron structure dictates the chemical properties and reactivity of given atoms. So the reactivity and chemical properties of any elements or any atoms depends on the electronic configuration, and electronic configuration in turn is determine the structure of an atom. So electronic structure is very important from the point of view of its properties and reactivity of an atom. So how do we determine the electronic configuration of an atom? So what is the criteria to determine the electronic configuration of an atom? So here we have the different principles which guide us or which lead us to fill the electrons in different orbitals. So one of them is Aufbau principles, then we have the Pauli exclusion principle, and then we have the Hund's rule. So these three are the most important principles which guide us how to fill the electron in the energy levels according to their energies. So now we are going to explain all these principles. So first of them is the Aufbau principles. Aufbau principles tells us that fill the energy states which depends on the value of principal quantum number and orbital quantum number. So it according to the Aufbau principles, we can fill the one electron at a time starting with the lowest energy state. So we will start first, we will fill the 1s electron, then we will fill the 2s, then 2p, 3s, 3p. So we can fill the one electron at a time starting with the lowest energy state. So this is according to the Aufbau principles. Then further filling of electron can be guided by the Pauli exclusion principle. Pauli exclusion principle further guides us about spin of electrons. That is, it tells us that we can't have the same 4 quantum numbers. So if you put one electron in and it spin up, and next has to be with the spin down. It tells us that if we fill the one electron in the 1s orbital, then the next electron must be with the opposite spin. So we cannot fill all electron in the state with the same quantum number. So all electrons should have the different quantum numbers, different 4 quantum numbers. So then there is the Hund rules. Hund rules further tells us that when electrons are added to the same energy levels, like we have the 2p energy level, 2ps, 2py, or 2pz. So the single electron enters the each states. So first we need to fill the 2px, and then electron will go to the 2py, and then will go to the 2p Z state. So it tells us that single electron enters each state before second electron enters in any state. So spin remains parallel prior to adding the second electron to any state. This means that we can interpret it like this. Home rules that tells us that first, for example, first we will fill the 2ps, 2py, and 2p electron with one electron with parallel spin, that is with this, for example, with the spin up state, and then we will fill the second electron with spin down state. Okay, let's explain the electronic configuration for the oxygen atom, for which Z is equal to 8. It has the atomic number Z is equal to 8. So how we will fill the electron according to these three principles, that is Oxford principle, Pauli exclusion, and von Rorschach. According to these principles, how we can fill the hydrogen atoms orbitals. So according to this principle, first we will fill the lowest energy state, that is 1s state. So first electron with the spin-off state, and then Pauli exclusion principle lead us that the second electron will be with the spin down state. So this state is completely filled state. Now we will go to the 2s state. So 2s state, again according to the Pauli exclusion principle, first electron will be with the spin up state, and then the second electron will be with the spin down state. Now we have the 4 electrons. Still we have the 4 other electrons to fill in the orbitals. So now we go to the 2p states. So according to Hund rules tells us that the electron are added to the state of spin same energies, then single electron enter each state before the second electron enter any states, and spin remains parallel prior to adding the second electron. So it means that now for the 2p states of the hydrogen atom, first we will fill first electron will go to the px, then will go to the py, and then will it go to the pz state. So to px state, second electron go to the 2py states, and third electron go to the p2pz state. So here you can see that all electrons are parallel in spin. So now we have 7 electrons. Still we have the 1 electron to fill in the orbital. So the 8th electron will go to the px state with the spin down states. So these here you can see that how these all three principles guide us to fill the electron in different orbitals in accordance with their energy levels, in accordance with their energies. Okay, now the electron configuration can be simplified by considering the core electron versus valence electron. As I have already told you that atom has the two types of electron. These are the core electron, that is the inner shell electron, or can be the outer shell electron, which are called as the valence electron. So the core electron, the electron in the inner shells, making up the noble gas configuration. So it's the noble gas configuration. So the inner shell electron are the complete shells, and the valence electrons in the outermost shells. The valence electron are exciting one, and in the sense that in general only the valence electron that participates in the chemical reaction. So these are the valence electrons. These are the very exciting ones because it's really gives the specific properties to the atoms by participating in the chemical reactions. So now we have the periodic table here right now, and here you can see that first we consider from the third period. For the third period we start from the sodium, and sodium atom have the electronic configuration like 1s2, 2s2, 2p6, and 3s1. As you can see that if we start from the hydrogen atom, for hydrogen atom we have the electronic configuration 1s1, and then we have here the 1s2, and here the 2s1, 2s2, and 3p1, 3p2, 3p3, 3p4, 3p5, and 3p6. So it's a noble gas configuration. For 3p6 we have noble, and then back when we come to the third period with the sodium atom, we start with the 3s1 and then with the 3s2, 3p1, 3p2, 3p3, and then we come at the argon at the end, which is equal to the 3p and 6. So for the sodium atom, it has electronic configuration of sodium atom is 1s2, 2s2 and 2p6 and 3s1. So we can write it like these are the core electron, because these are the complete shells, that is for sodium atom up to here, that is these are the core electron, and then for we have the 1s1. So for the core electron 1s2, 2s2, 2p6, these makes the noble gas configuration. So we can write it in the sodium like, so these are the valence electron, 1s electron is the valence electron, others are the core electron. So we can rewrite the electronic configuration of sodium atom like sodium is equal to neon and in times 3s1. So core electron configuration is neon, that is noble gas configuration, and then we have the 3s1. So as we go along the third period, from after sodium we have the magnesium. For magnesium we have the configuration neon and then 3s2, and from magnesium when we go to the aluminium we have the 3s2 and then 2p1 up to so on. When we go to the silicon we have neon into 3s2, 2p2 and then 2p3, 2p4, 2p5 and up to so on. When we reach at the argon we have the 2p6. So we can write at argon, which is the last element of the third period, its electronic configuration is neon, 3s2 and 2p6. So we can write the electronic configuration. We can, as we go along the period in the periodic tables, we can add the electron into the different, we can add the electron in the atoms in different orbitals. So same thing explained for the third period, for the fourth period. Fourth period, at the period of periodic table, we start from the potassium, that is K, and as we know that here the last element of the third period is the argon. So argon has the electronic configuration ends with the 3p6 orbital. So with the fourth period we start with filling the electron in the 4s1 orbital. So for the potassium is equal to the argon into 4s1, and after argon we have the calcium, we have the 4s2, and then we come to the scandium, and then is equal to the 4s. Here we start with the transition metals and we start filling the electron in 3d orbitals. So we have the electronic configuration 4s2, 3d1 and then 4s2, 3d2, 3d3 up to so on when we reach at the chromium. So there is the exception to Aufbau principle. So instead of having the electronic configuration like 4s2, 3d4, we have the configuration like 4s1, 3d5 up to so on. We can fill the electron iron, for iron, cobalt, nickel, copper, zinc, and then up to so on. At the copper we have another exception. So instead of having the 4s2, 3d9, we have 4s1, 3d10, and then zinc up to so on, gallium. So we have the last element of this fourth period, we have the Kr, and so here they have the electronic configuration AR in 4s2, 3d10 and 4p6. So it is again the noble gas configuration. So we can fill the electron along the period as we go along the periodic table. So next thing is using this chart. So here we have the chart. We can write out the correct order of the orbital with increasing energy level from left to right in the periodic table. So this one is the chart. Here you can see that we can fill the electron in the period along the periodic table. First we fill the 1s, then 2s, 3s, 4s, 5s, 6s, 7s, and then we have the 2p, 3p, and so on. So how we will fill the electron using this chart? So the first we will fill the 1s electron, and then 2s, and then from 2p 3s, and then we will fill the 3p 4s, and then 4d 5p 4p 5s. Next will be the 4d 5p 6s, and then 4f 5d 6p and 7s. And then we have the 5f 67p electron, and then 6f 70 electron. So using this chart we can write the electronic configuration like 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and then 5s, 5s. Then we have the after 5s we have the 4d, 5p, and 6s. So in this way we can flow the electron by using this chart. So you can write the electronic configuration easily by using this. So thanks for watching. For more video please subscribe our channel.